So here we've got 0.3 molar lead 2 nitrate. Could you hold that up for the camera, please? There we go. And we've got 0.3 molar HCl. Thank you, Taylor. So now what we're going to do is we're going to measure out 5.0 mils of the lead 2 nitrate, and at the same time here, Taylor will measure out 1 mil, or 1.0 mils of the 0.3 molar HCl. Now, if you don't have dropping bottles here, then you can use a pipette to make this measurement. And the idea is to try and get the meniscus, you have the bottom part of the U, onto the line you need. So 5 for Sam and 1 for Taylor. Alright, so go ahead now and pour both of those into a test tube. Yeah, make sure the test tube is a fairly largish one. Could you put that next to the graduated cylinder just so we can get an idea? See, something a bit bigger than that, which is good. And we're looking for a precipitate here. And if we bring this up to the camera, could you bring it up to the camera? Right. You can see if there's no precipitate. Taylor, go ahead and measure out another 1.0 mils of the HCl. Okay, go ahead and add that into the solution here. And let's give that a little bit of a stir, please, with the stirring rod. We see some particles here, don't we? Could you bring this up to the... Yeah, bring this up to the camera, please. A little bit higher. There we go. Yeah, that's nice. Alright, let's go ahead now and stick this into the hot water. And what we're going to do is we're going to see if we can get this precipitate to dissolve. Just leave the stirring rod in there, please. I'm going to zoom in here on the solution. And every so often, Samuel will give that a little bit of a stir. How are we looking?
It's almost gone.
Almost gone? Okay.
A little bit on the bottom.
I'm sorry?
Just a little bit at the bottom.
Okay. Alright. It's good. Okay. Looks like it's dissolved, right?
Yep.
So let's go ahead and could you please put the cold water out the front there? That's good. Okay, let's go ahead and stick that into cold water. So we saw it dissolve in the hot water, and now we're going to see what it does in the cold water. And we'll wait a couple of minutes here, and if we see a precipitate, then we're going to start adding 1 ml portions of cold water to see if it dissolves or not. Okay. Alright, now we can go ahead and stir it, Sam. We'll see if they've got any precipitate going here.
Yeah, there is.
Yeah, I think I can see some on the bottom there. Yeah, I can see a little bit. Yeah, I can see it there, sort of swirling around. Alright, good. Let's go ahead now, Taylor, and please add 1 ml amounts of DI water to that. We can go ahead and take that out of the water bath now, Sam, while we're adding the 1 ml portions. Okay, so make sure you're in the shot, please. There we go, that's good. Okay, let's go ahead and add that. Okay, give it a bit of a stir around, please. So what we're going to do is continue adding 1 ml portions until it dissolves. Making sure you count them. Alright, that's good. Put another one in. Looks like there's still a little bit of solid in there. Go ahead. And give it a bit of a stir. And it looks like it's dissolved. Alright, could you bring that up to the camera please? And you can see that's pretty much dissolved now. That's good. Thank you. So I want to give you some guidance as to what's going on before something precipitates and what's going on after it precipitates. And we're going to be talking in terms of the KSP value and the Q value that we have for this as well. Yeah, I'm going to change that a little bit. I'll make it QSP just for the sake of consistency. So we've got our PbCl2, and you can see that if we drew a picture of it, it would consist of Pb2 plus and 2Cl minus ions. So when it splits apart in solution, we'll start off with a solid and we'll end up with Pb2 plus aqueous and then 2Cl minus aqueous ions along with that. So we can measure this KSP value, which is going to be Pb2 plus and Cl minus to the power of 2, and you can see where the 2 comes from the coefficient here. And what I want to get across here is that it's at this point where the precipitate is just dissolving or where it is just appearing. So if there wasn't precipitate before and you're just beginning to see it now, that's the KSP point. Or if you had precipitate and you are dissolving it by adding water, then the point where it's just dissolving, that's the KSP as well. So these concentrations at that point, the Pb2 plus and the Cl minus squared, will determine what the KSP value is. But we have to know if the precipitation is occurring or not occurring. So let's see exactly what we were doing in this experiment. So we start off where we have Pb2 plus ions in the solution, and they're going to have a certain concentration associated with them. But what we're doing here is we're adding Cl minus ions into the solution, and we're doing it fairly slowly, because remember we add just a mil at a time, right? So what's going to happen is if the concentration of Cl minus is insufficient to get to the KSP value, then everything's going to stay in solution. So the rule is this: if QSP is less than KSP, then no precipitate. But of course, if we keep on adding Cl minus into the solution, eventually what's going to happen is that it will precipitate, because we'll form this solid here, we'll get to this KSP point, but only once enough Cl minus has been added to make that happen. So if QSP is greater than KSP, then precipitation will occur. And that's exactly what you would have observed while you were doing the experiment. Now the other thing you did was you took the solution and you heated it once you had a precipitate form. And what you need to do now is determine whether or not your reaction here is going to be an exothermic one or an endothermic one. So I've got two examples over here. I've got A plus heat gives B. That would be endothermic, and delta H for that would be positive. If A gives B plus heat, then that would be exothermic, and the delta H would be negative. So we can actually figure out what's going on, and this was the clue that I would give you here. If the precipitate dissolves when solution is heated, what I want you to do is figure out which side the heat would be on. Would it be on the reactant side or would it be on the product side? Well, my clue would be if you've got solid and you heat it and it dissolves, because this would be solid and this would be dissolves because now you've got ions, and heat caused that, I wonder which side the heat would be on. And then from there you could figure out whether it's endothermic or exothermic. So as you just saw with that experiment, what you did was you added a certain amount of lead nitrate to a solution, then you added some HCl to the solution, you got a precipitate, and then you added enough water to just make it to the point where the precipitate dissolved. So what we're looking at here is the equilibrium of PbCl2 interacting with these aqueous ions of Pb2 plus and Cl minus. So you can see if we have PbCl2 and we drew a picture of it, it would be Pb2 plus and then 2 Cl minus ions. So you can see that that's how it would break apart in solution. But if we've got it just at the edge of precipitation, which is what we did in the experiment, if we know what the concentrations of these ions was at that specific point, after you've added the water, it just dissolves, then what we can get is this KSP value, which gives us an idea of the equilibrium constant responsible for this solution or dissolution process that we're talking about here. And that's what we're going to aim to find. In order to do that, though, we need to know what the concentration of Pb2 plus and Cl minus was at that very point after we've added the water. Now, because we have an initial concentration here of 0.30, that won't be valid once we've added all these other bits into the solution, because now we've diluted the solution. So we need to be able to have a way to calculate that Pb2 plus once we've gotten to that point where we've added this extra water. So what we do is we'll find the moles of Pb2 plus. That won't change in the solution. Now we can get that by taking the concentration of Pb2 plus, which is 0.30 moles per litre, and multiplying it by the actual volume that we're using. In this case I've put 10 mils. I think you'll use something different in the lab, but I'm just doing this as an example. And you can see that milliliters and the litres won't cancel, so we have to do a conversion here. So it'll be 1 litre over 1,000 mils. And you can see by doing that, the mils cancel and the litres cancel. We're just left with moles, which would be 0.0030 moles of Pb2 plus. So that's not going to change in the solution. The moles of Cl minus will get similarly. You can see we've got a concentration of HCl here. Remember that HCl splits into H plus and Cl minus 1 to 1, so we'll be able to get the moles of Cl minus that way. The other thing we're going to need to do now is find the concentration of Pb2 plus in the new solution, or in the solution just as it reaches that point of dissolving after it precipitates. And the way we're going to do that is we're going to take the moles that we have of the Pb2 plus, and we'll divide it by the total volume, which is going to be in litres. And the way I get that is by doing 10 plus 5 plus 10 is 25 mils. So it's going to be 25.0 mils. I'll do a conversion to get that into litres. And the concentration of Pb2 plus then would be 0.12 molar. The concentration of Cl minus we'll get by a similar method. After we've done that, you can see that we can get the Pb2 plus, we can sub it in here. We've got the Cl minus, don't forget to square it, and that will allow us to do the multiplication here and come up with our KSP value. So what Sam's got in his hand here is a Conc HCl dropping bottle, and I want to give you an idea about how to use a dropping bottle. Sam, could you bring that closer to the camera please, and sort of point it towards the camera so I can see the knob on the top there. So you see it's got this little nub here. Now down the side here it's got these channels as well. So what Sam is going to do is he's going to turn the top there and make it so it's in line with one of those channels. Now the story is that HCl can travel in the channels, and there's a little channel here in the knob as well, and it's going to come up here and sit down on the side. Alright, so let's go ahead and put that down now, Sam. And now what Samuel's going to do is he's going to get a little bit of the cobalt chloride hydrate. Now we've already measured out 0.1 of a gram, and we've pretty certain that, hang on, let me zoom in on that. You can see how much he's got there on the end of that small spatula. That's about 0.1 of a gram, because we already measured that out to see what that would look like. So that's a good guidance there for you. Now if you want to weigh out the 0.1 grams, that's fine, but I don't really see the need to, because we're not really that interested in the amount. Alright, go ahead now and add that to the test tube. Alright, that's good. Thank you. Now we need to add about 2 mils of this concentrated HCl. So you can see what Samuel's going to do. You know, he's putting his hand or his finger on the top there, and that's important. That's so that the top doesn't fall off. And I'm going to zoom in on that so you can actually see the drips going in. There we go. And you can see it's just dripping through. He's putting about 25 drops in. That's going to be equivalent to about 2 mils. Alright, sorry. So let's give that a bit of a swirl here, please, Taylor. And you can see it's a nice blue colour. Yeah, that's nice. Alright, that's great. Okay. So now what Samuel's going to do is he's going to add 2 mils of water to this cobalt chloride solution that we've created. It's currently deep blue colour. Go ahead and add the water, Samuel, and see what happens. Oh, give it a little bit of a swirl. Oh, looks like it's changed colour, doesn't it? Alright, so in the next step, what we're going to do is we're going to put this into hot water and see what happens then. Right. So we've got our solution now. Could you please put it in the camera? A little bit higher. There we go. So there's our solution. As you can see, it's a pinkish colour. And now what we're going to do is we're going to put it in hot water. Now go ahead and do that, please. I've got it in a 250 ml beaker, and it's, as you can see, there's bubbles on the bottom, but it's not quite boiling yet. So we're going to leave that in there for about 3 minutes, and I'm actually going to leave this. Sit while, and so you can see what happens while we're heating it. Go ahead and zoom in. Would you please give that just a tad of a swirl, please, Sam? Okay. That's good enough? Okay, go ahead and put it back in. Probably not really necessary to swirl it, but you can already see what's going on with this. It was a pink colour, now it's a kind of a magenta, I suppose. But we're going to leave it in there a bit longer, we'll see what happens to it. Want to leave it in there for about 3 minutes. It's been in there for about a minute now, right? Alright, so it's been about 3 minutes, hasn't it? Mm-hmm. Okay, let's go ahead. Could you please put that in front of the hot plate here? Right, this is just cold water. We're going to stick this into the cold water and we'll see what happens. Give it a little bit of a swirl, please. And you can see what's happened was it was blue. Now it's gone back to red. Okay. This is some guidance for part B. So first of all, let me define what I mean by cobalt complexes. Cobalt complexes are compounds of cobalt, and the two that we're dealing with here are the one that has water as the ligands and one that has Cl as the ligands. Those are the things joined to the CO. But the point is that they have different colors. The one with the water has pink, the one with the Cl or Cl minus has blue. And what that means is if the reaction is more on the reactant side or going towards the reactant side, it turns pink. If it's going to the product side, then it turns blue. Now that really is all you need to know about that. Now the thing is that by adding or taking away certain of these reactants, we can go from one side or the other. So I want you to think about what would happen if we added Cl minus, which way the reaction would go. Or if we took Cl minus away. Well, let's say we took Cl minus away. What would happen is that the reaction would turn pink because the Cl minus was disappearing and the products would like to create more Cl minus to replace that Cl minus that you took away. So that's just one example. But you can tell which direction something went by looking at the colors, and you definitely know what the colors are in these processes. The other thing that we can look at is whether the reaction itself is going to be exothermic or endothermic. So the two possibilities are these here. We've got A gives B plus heat, that's exothermic, that would mean delta H is negative. And if it's endothermic, that would mean delta H is going to be positive. So the one where the heat is being formed as a product, that's going to be exothermic. The one where heat is a reactant would be endothermic. Now how you can tell is if you were to heat the reaction and it turned a certain color, then the color it was originally before it was heated, and then if you knew what color it was after it was heated, then you could figure out which side the heat was on, because the heat is causing the color change. And that would be my hint to you about that.